Hi, my name is Angwei and I'm a fellow in the System Design and Management program at MIT. Today, I'll be presenting on the topic of my master's thesis, which is smart contracts and their application in supply chain management. I'll first provide some background and talk about the challenges in supply chain management. I'll then give a brief introduction to blockchain technology and smart contracts. Next, I will touch on how smart contracts can be used to solve challenges in the supply chain. After that, I will describe a proof of concept that was developed and tested on the Ethereum platform. Finally, I will conclude and discuss the way ahead. A supply chain refers to the network of all the individuals, organizations, resources, activities, and technology involved in the creation and sale of a product. This involves multiple processes, from the procurement of raw materials by suppliers, to design and fabrication by manufacturers, delivery of the finished product to consumers, and can even include post-sales logistics support. Supply chain management integrates all of these steps and orchestrates the people, processes, and technologies required to ensure a smooth flow. As can be seen from the stakeholder value network that was generated for a generic supply chain, there are several stakeholders involved. They range from those on the supply side, such as suppliers and manufacturers, to those on the demand side, like distributors, retailers, and consumers. And even non-market stakeholders that may not be directly involved in the market for the product, but can still influence it. For example, regulatory authorities and NGOs. Multiple exchanges take place between the stakeholders, and these exchanges can be financial, goods or services, information, or political. All of these add to the complexity of supply chains. Given that supply chains involve complex networks and multiple processes, there are many challenges associated with managing supply chains. These challenges can be broadly categorized into two stages, the planning stage and the coordination stage. The planning stage involves determining the level of supply and demand, whereas the coordination stage concerns the actual physical movement of goods. This presentation will focus on the coordination challenges. The first is information sharing and product traceability. Given the multiple stakeholders across the supply chain, it is inevitable that information asymmetry exists. Whether this asymmetry is intentional or not, it poses a challenge in managing the supply chain without complete information. An example of the lack of information sharing affecting the supply chain is in product traceability. Without the availability of real-time information to track progress through the production cycle, it is difficult to update forecasts and respond swiftly to negative events. If the product is delayed or there is insufficient supply to meet demand, this could jeopardize future customer relationships and have a longer-lasting detrimental effect on the organization's brand. The second challenge is managing risks and disruptions. This is especially crucial for supply chains given the wide geographical and organizational spread. In an increasingly volatile world where natural disasters or production disruptions can occur at any time, supply chain managers must have adequate backup plans to ensure that the supply chain is flexible enough to handle sudden changes without too much delay or impact to profits. Another way to manage risks and disruptions is through increased visibility along the supply chain, as this will allow organizations to remain nimble and stand ready to respond quicker in the event of a disruption. Third, as the regulatory environment and consumer behavior continue to evolve, there is a push towards greater transparency in the provenance of goods and the supply chain process as a whole, in order to better ensure product safety and manage recalls. Consumers have also become more discerning about the products that they buy and often choose products that are aligned with their values and beliefs. For example, people might want assurance that the product originates from a reliable source, that does not use child labor, does not harm the environment, or does not engage in any other unethical practices. Since it is essential to manage the customer relationship, having a means to ascertain the provenance of a product is increasingly important. Greater transparency also helps to keep parties in the supply chain accountable, as they are obliged to adhere to the standards set rather than cut corners for their own gain. Finally, and related to the other challenges, is the need to build trust across the supply chain. Sharing of information and increased transparency have shown to increase the level of trust among supply chain partners. In turn, trust helps to foster commitment as parties are more aligned with a common goal and values. In addition, trust can provide a competitive advantage. When all parties are on the same page, the supply chain will be more flexible and can adapt to situations and make decisions faster. One way to engender trust is through building up and maintaining a good reputation. If suppliers have proven over time that they are reliable and produce high-quality products, manufacturers are more likely to trust them. Similarly, suppliers will feel more comfortable working with manufacturers who have shown that they keep to their word and do not alter requirements at the last minute. We can potentially leverage new technologies to address these supply chain management challenges. One such technology is blockchain and its associated smart contracts. At its core, Blockchain is a distributed ledger technology that leverages the resources of a large peer-to-peer network to verify and approve transactions. These transactions are recorded chronologically in blocks, and the blocks are linked together cryptographically and stored permanently on the blockchain, creating an immutable chain. There is no single copy of the blockchain. Rather, copies are distributed globally across the participants in the network and updated simultaneously. This ensures that the ledger cannot be manipulated by any single party without the consensus of the majority in the network. The type of information stored in the transactions can be varied. For example, currency, intellectual property, identity data, or location data, to name a few. This makes blockchain technology highly customizable for different applications. One benefit of blockchain is its immutability. Once a transaction is recorded and propagated to the network, it becomes permanently stored on the blockchain and can be accessed subsequently for verification. This provides an audit trail for reliable verification. Since each block is linked to the preceding block, this also discourages rogue parties from manipulating the transaction records, as they would require massive computing power to change all the subsequent records and obtain a majority consensus. Collective interest helps to ensure the blockchain's safety and reliability. Blockchain can also reduce two key costs: the cost of verification and the cost of networking. Whenever an exchange of value occurs, key attributes of the transaction need to be verified by the parties involved. This usually involves a trusted intermediary, which typically charges a fee for providing verification services. In addition, they may also require some form of information disclosure from the parties involved, for example, social security number or credit card information. This increases the risk of data leakage should the intermediary's security be compromised. Blockchain can circumvent this by securely storing key transaction attributes on a distributed ledger and allowing them to be verified at a future time without incurring additional cost. The cost of networking can also be reduced by combining blockchain's distributed ledger technology with a native cryptographic token such as Bitcoin. The token can be used as an incentive to grow and secure a new platform, and an entire marketplace can be bootstrapped without the need for a costly intermediary. This can also allow participants to achieve large-scale consensus on the allocation of scarce resources. For all of its benefits, blockchain also has some limitations that need to be overcome before it can become more scalable. First, the proof-of-work protocol used to generate blocks is computationally wasteful by design. Although this may help to preserve the integrity of the blockchain by deterring attacks, a large amount of resources and energy need to be committed. As the chain grows longer, even more computational power is required, exacerbating the problem. Second, as larger blockchains require more resources, processing speed is also adversely affected, as more time is required to verify and approve transactions. To provide a comparison in financial applications, an established intermediary like Visa can process more than 50,000 transactions per second at peak, whereas Bitcoin can only process 7 transactions per second. Hence, blockchain's computational efficiency must be increased significantly before it can seek to challenge the incumbents. Third, even though blockchain technology relies on consensus of the majority to ensure security of the system, it is not completely immune to security breaches. Exploiting the need for consensus, it is plausible that a single rogue entity could garner enough share of the network to achieve slight majority, when it would then be able to introduce its version of the blockchain and validate it. This is also known as a 51% attack. Although this is unlikely due to the distributed nature of blockchain, it is not impossible, especially as computational requirements grow, making it commercially viable for only a small number of influential participants to continue mining for reward. Another problem that could arise is if users are able to exploit security flaws in the code underlying a blockchain. This occurred when a hacker exploited a weakness in the code of the DAO, a blockchain-based venture capital fund, and was able to siphon one-third of the cryptocurrency that it had raised from investors. Although the flaw was fixed subsequently, it has affected confidence in blockchain's viability on a larger scale. To date, the most prominent implementations of blockchain are in cryptocurrencies such as Bitcoin and Ethereum. In particular, Ethereum aims to take blockchain technology beyond finance and serve as a platform for decentralized application development that can be used for a myriad of industries. Ethereum's differentiating factor is that it is programmable to suit users' requirements, rather than giving users a set of predefined operations. As a result, it could in theory be used to automatically and reliably carry out any transaction involving trust, security, or permanence. One way to do this is through the use of smart contracts, which are digital agreements between transacting parties, written using computer code and programmed to self-execute when certain conditions are met. These can be integrated onto a blockchain platform like Ethereum to provide the verification and integrity necessary for such an automated system to work. Here's a summary of how smart contracts work. To create a smart contract, parties must first identify an opportunity for them to collaborate and agree on the desired outcomes for each party. This could include any possible exchange of value such as goods or services. Next, they must set the terms and conditions that have to be met in order for an exchange to occur. These could be triggered by the parties themselves, by external events, or by certain milestones. All of the requirements and contractual agreements are then programmatically written using computer logic and code. The smart contract can then be deployed to the blockchain, where it will self-execute when initiated by the specific conditions. In order to initiate a smart contract, users must use their account on the blockchain to carry out a transaction with the deployed contract's account. This is encrypted with the initiator's private key and transmitted to other nodes in the blockchain. The other users can verify the authenticity of the transaction using the public key generated to ensure that the initiator was indeed the one who triggered the transaction. Once consensus has been obtained from the majority, the transaction is added to the blockchain, the smart contract is successfully executed, and its outcomes are recorded. As the state of the blockchain changes, it is updated across all nodes in the network, and the outcomes cannot be altered. Due to the computational resources required to maintain the proof-of-work system, every transaction that creates a change in state in the Ethereum platform, including deploying and executing smart contracts, requires a transaction fee. This is paid by the initiator of the transaction in the form of Ether, Ethereum's native value token. The amount depends on the extent of computing power and memory storage the transaction requires. This discourages frivolous or malicious computational tasks and provides impetus to write smart contracts with as efficient code as possible. Many use cases have been advocated for smart contracts. This includes financial technology, such as securities and derivatives trading, digital identity management, property, to manage mortgages and for land title recording, insurance, to automate the claims process, and medical, for management of patient data and sharing of research. However, the key use case that I will be focusing on is the application of smart contracts in supply chain management. Smart contracts can improve supply chain management in three key ways: transparency, traceability, and efficiency. Smart contracts can enhance transparency in the supply chain by recording the provenance of goods. By storing information such as the date, location, and quality on the blockchain, the origin of a product can be easily verified. This will provide assurance to manufacturers that their raw materials are coming from reliable sources, and consumers can have more confidence that they are purchasing a legitimate product. By allowing a digital form of identification to be created and stored on the blockchain, smart contracts can also help with transparent credentialing across supply chain partners. Parties will be able to easily verify that other parties have the requisite certifications to carry out their duties. Reputation and reliability can be recorded and managed on the blockchain as well. This will allow supply chain managers to make more informed decisions when selecting suppliers, and also spur suppliers to work hard to maintain a good track record. In addition, this may also provide a platform for lesser known but quality suppliers to increase their global reach. In a sense, the playing field becomes more level and meritocratic. Another benefit is that blockchain ledgers establish a shared, secure record of supply chain information flows, a single version of the truth across networks for supply chain transactions, processes, and partners. Product, transportation, and accounting information can all be stored on the blockchain and accessible to relevant parties. This openness helps to ensure that all parties are on the same page and reduces the potential for conflict. Should there be disputes, they can also be resolved faster since there is a common database to refer to. Smart contracts can improve traceability within the supply chain by allowing inventory to be tracked at every step along the way, from its raw material source to end-user delivery. One way to do this is through the use of smart sensors, which can provide a wealth of data such as location, environmental conditions, and even product quality. With more information and real-time updates on product status, supply chain managers will be able to make better and faster decisions. This can help to reduce delays and keeps the supply chain agile. Organizations will also be more well-equipped to deal with disruptions like natural disasters, factory strikes, or delivery accidents. In a world with increasing product competition, being able to maintain continuity of supply can go a long way towards enhancing consumer confidence and their impressions of a brand. The ability to trace the chain of custody of inventory through the supply chain becomes especially useful in the event of product recalls or safety incidents. This is evident in incidents such as the Chipotle food poisoning and Takata airbag scandals. The issues could have been managed more efficiently and the damage could have been contained had the companies been able to identify the root of the problem earlier. Using smart contracts in the supply chain can enhance efficiency in two aspects: process and cost. Process efficiency is improved as smart contracts executed on a distributed ledger help to simplify the complex multi-party systems present in typical supply chains. Given their self-executing nature, smart contracts can be used to automatically execute contractual rights and obligations, including the terms for payment and delivery of goods and services. This eliminates much of the cumbersome paperwork traditionally required and reduces time wastage. By programming the contracts to execute only when certain milestones are met, parties can also be more trusting and not have to worry about unfulfilled obligations. The other way efficiency is enhanced is through cost reduction. Relying on trusted computer code that is easily customizable to execute contractual agreements precludes the requirement for numerous physical documents that need to be maintained by each party's purchasing, accounting, or legal department. This helps to lower costs and the amount of manual effort undertaken. Having a database where identity and reputation can be easily verified also saves on costs associated with conducting certification checks and building new trusted business relationships. Clearly, smart contracts have the potential to bring many benefits to supply chain management, and I am proposing a concept to test this. To develop the proof of concept, I used Solidity to write the smart contracts. Solidity is an object-oriented programming language that is widely used for writing smart contracts. Its syntax is similar to that of JavaScript, and it is designed to target the Ethereum virtual machine. The proof of concept consists of 3 different smart contracts that address 3 main challenges in supply chain management. The first is to determine the provenance of goods. The second is to track the progress of goods through a supply chain. And the third is to build trust through maintaining an open database of supply chain partners, including their reputations. To help illustrate the concept, I assume the following simplified supply chain for a basic consumer electronic product. The OEM in red is the focal organization and is in charge of coordinating the supply chain. The other parties are designated as either supply side in green or demand side in blue. Supplier A sources the raw material and ships it to supplier B, who manufactures the individual components. The parts are then shipped to the OEM, who assembles the final product. The product is shipped to the distributor, who distributes it to the retailer to sell to the consumer. The proposed concept will run on a blockchain that all supply chain partners will be able to access, and consumers can gain access to certain functions such as checking provenance. It can be deployed and administered by either the focal organization or a neutral third party, such as a blockchain startup like Provenance or Modem.io. For the provenance smart contract, supplier A, the origin of the supply chain, will be required to record its details and the details of its raw material to the blockchain. Through integration with a smart sensor, the location and time from which the raw material is shipped can be immutably stored. This will allow any of the other parties, including the consumer, to access the information through the blockchain. By providing a quick way to determine provenance, raw material providers are kept accountable and parties can easily verify the source of their product. For the tracking smart contract, each party will be required to record the details to the blockchain whenever they send out a shipment or receive a shipment. When a shipment is received, the receiving party will confirm that everything is in order. If the shipment arrives on time and at the correct location, as verified by smart sensors, a payment in the form of crypto tokens is triggered to the shipping party. An example is illustrated in the figure shown. In step 1, the OEM predetermines the acceptable lead time and correct location for each leg of shipment. It also holds all the crypto tokens initially. In step 2, supplier A records the details on the blockchain when it ships raw material to supplier B. When supplier B receives the shipment, it records the details in step 3. The smart contract then checks that the shipment tallies and whether the predetermined criteria have been met. If everything is in order, in step 4A, a payment is executed from the OEM to supplier A, as shown by step 5. Otherwise, an alert is triggered so that parties can rectify any problems, as shown in step 4B. Automated tracking and payment will help to simplify the processes within the supply chain and provide real-time updates on product status, so that parties can remain agile in the event of unforeseen circumstances. For the reputation smart contract, all parties in the supply chain are required to record their details on the blockchain. In addition, a reputation score can be reflected. A simple way to determine reputation of a party is to calculate their number of successful shipments as a percentage of their total number of shipments made. The number of successful shipments in this case is defined as having the correct item and quantity and delivering it on time and to the correct location. This can be included as part of the tracking smart contract, and the reputation smart contract can access the reputation score by calling the other contract. This can then be updated as more shipments are made. To make it more convenient to browse the list of suppliers, functions to filter by the type of goods and reputation are also included. The open database will incentivize parties to work towards maintaining a good reputation and help build trust among parties with greater transparency. Here is a summary of the functions contained within each smart contract. The provenance contract is accessible to supply chain partners and consumers. It can be used to record producer details to the blockchain, certify producers, retrieve producer details, record product provenance details to the blockchain, and retrieve product provenance details. The tracking contract is accessible to supply chain partners only. It can be used to set predetermined criteria for fulfillment of shipments, record shipment dispatch and arrival details to the blockchain, automatically execute payment in the form of tokens for fulfilled shipments, retrieve shipment details to get a status update, and calculate the reputation score for parties. The reputation contract is also only accessible to supply chain partners. It can be used to record supplier details to the blockchain, retrieve supplier details, retrieve a list of all suppliers, retrieve the reputation score of parties, update reputation scores, and search for suppliers by either the type of goods or their reputation score. The arrows between the tracking and reputation contracts indicates their interactivity when deployed on the blockchain, since the reputation score information is shared between both contracts. Further details on how each function works can be found in the main paper of the thesis. Remix, a browser-based Solidity compiler and integrated development environment, was used to provide a preliminary validation of the proof of concept. It simulates the Ethereum virtual machine, containing all of the tools necessary to create, compile, deploy, and test smart contracts, as they would be done on the actual Ethereum network, but it does not actually connect to the live network. Since deploying contracts and executing transactions on the live Ethereum blockchain incurs costs in the form of Ether, Remix provides a developer-friendly environment to iterate, test, and debug contracts without actually incurring real transaction fees. Its intuitive web interface also allows for quick and easy testing to be carried out. Contracts can be deployed and transactions executed with simple button clicks, and the output and costs are displayed correspondingly. 5 test accounts are also available, so that different parties in the supply chain can be simulated when testing the contracts. All 3 smart contracts were comprehensively tested using Remix, and all of their functions work as intended. In addition, the use of events helps to clearly indicate when pertinent transactions have occurred. For example, when goods have shipped, when goods have been received, or when payment has been executed. They also trigger alerts whenever certain transactions are unsuccessful, so that parties can identify the problem quickly and easily, and work towards rectifying it as soon as possible. This is more efficient than manual systems currently in use, where errors can go unnoticed for long periods of time. Having a standardized contract template also ensures that all parties share information in the same way. This reduces the risk of misinterpretation or loss of information due to different types of forms used, and eliminates the need to maintain different methods of data entry. In conclusion, the proof of concept provides a simple way to address some of the coordination challenges in supply chain management. It increases transparency by recording the provenance of goods and certification of supply chain partners on the blockchain, so that the information is easily accessible to all parties, including consumers. This can provide assurance that the goods are coming from legitimate sources and will be helpful in the event of disruptions such as food safety recalls. The proof of concept also improves traceability, as the chain of custody of goods can be tracked as they are shipped along the supply chain. Real-time updates help to manage risk by keeping the supply chain agile and ready to respond to any disruptions. By integrating automatic payments with successful delivery of goods, supply chain efficiency is enhanced as well. Finally, having an open database with details and reputations of all supply chain partners helps to build up trust within the supply chain. Parties will not have to waste time and money for extra verification checks, and are also incentivized to work towards maintaining a good reputation. Looking ahead, further testing can be carried out on Ethereum's test network as well as actual live network. This will provide a more accurate representation of the transaction times and costs involved. Another step would be to integrate the smart contracts with actual data from smart sensors. Since Ethereum requires all nodes to agree on the outcome of a computation, the smart contracts can only execute strictly deterministic functions and cannot perform native operations, such as random number generation or API calls. Hence, in order to obtain external data such as those from smart sensors, they need to rely on oracles. An oracle or data feed is a trusted third-party service that sources real-world data that is requested and pushes it to the blockchain to be used by smart contracts. Specifically, hardware oracles obtain information from the physical world, such as smart sensors. Finally, the reputation score calculated in the proof of concept is a very simplistic way of representing the overall reputation of a party, since it is only based on the proportion of successful shipments made, or shipment history. A more sophisticated mechanism can be explored, perhaps using additional factors such as reliability, online reviews, or product range. This can help to provide a more robust and accurate representation of a party's reputation. I would like to thank Dr. Abel Sanchez, my thesis supervisor, without whom this thesis would not have been possible. I would also like to thank the staff and my fellow peers in the SDM program for all of their support and enriching interactions. Finally, I would like to thank my family and friends who have stood by me and given me encouragement throughout the entire process. Thank you.